So let us begin. Let us begin my second session of today's class. And in this class, I'm going to talk about. In this session, I'm going to talk about how to solve a linear programming problem. Since your syllabus is consisting of only simplex method, but I don't think it is a good idea to start from simplex method without understanding something else. And so here in this particular class, I'm going to talk about graphical method of solving a system of inequation. Now, graphical method has one drawback. This method can only be applied when number of variables present is less than or equal to 2. How to solve L.P.P using graphical method? Okay. Graphical method can only be applied if the number of variables present is less than or equal to 2. Okay, if a number of variable is less than or equal to 2, then you can draw a two-dimensional figure, isn't it? And then you can very easily analyze that. There was one book by some author, I forgot his name, he was from India and from Bengal Engineering and Science University. In his book of operations research, he showed how to solve graphically a system consisting of 3 variables, and if 2 variable system gives you 2-dimensional figure, then 3 variable system will give you 3-dimensional figure. So he drew 3-dimensional figures and marked the regions accordingly, and very hectic job. So such a thing will not be done in the class. I am going to talk about only 2 variable system which can be solved by graphical method. And to make you understand that, I am going to consider a very simple problem just to say what is the methodology of doing that. But not only this, when I'll be teaching you what simplex method is, then you are going to get some sort of close connection between this graphical method and simplex method. First of all, in simplex method, I'm going to deal with a system consisting of 2 variables. Then I can move forward to 3 variables. And if you can solve a graphical, if you can solve a system with the help of graphical method, then once you solve it by simplex method, you can correlate the 2 answers. You can check your answers accordingly. Okay, so that's why let us stick to the 2-dimensional problem for the time being. So for example, let us consider the problem as follows. I am not considering the previous problem. The reason for which will be told to you later. So my problem is, say for example, I'm just giving it from my mind. Maximize z is equal to say for example 2x plus 3y. Okay, and subject to, I'm considering the constraints as x plus y is less than or equal to 1, and 2x plus 2y less than or equal to 4. Okay, and x comma y greater than or equal to 0. Suppose this is my problem, and I have been asked to find the values x and y. I'm going to apply graphical method to solve this linear programming problem. You can very well understand that this part is called the objective function. Okay, and since it is a maximization type of problem, you can consider this to be profit. Okay, and these are the decision variables x and y, and these are the constraints. Okay, and this is the non-negativity restriction. Every item, every important part of the linear programming problem is present over here. Step number 1 is, and students, I am telling you one thing, that operations research problem is algorithmic based problem, and the methodologies are too clumsy, too hectic, too tedious. So you have to have some sort of patience to deal with that. Okay, if you lose patience, then you will not be able to understand anything. Okay, so just hold on and listen to me very carefully. Okay, so first of all, in step number 1, you are going to draw two straight lines, which are nothing but the x-axis and y-axis, which are x-axis or y-axis. Okay, now let us put here y and let us put here x, and suppose this is my origin y, origin O. So step number 1 is draw axis. Step number 2, put straight lines. Put straight lines. You know that although these are inequations, all these inequations, if I omit, for just in my mind, if I omit the inequality part, and if we consider the equality portion only, and since these equations are linear equations, so actually they represent a straight line. So here I'm going to talk about something which is a prerequisite kind of thing. You know from your earlier experience that if ax plus by equals to c represent a straight line, okay, then easy way to draw it. And if I ask you to draw the straight line, what you can do, you can keep y on the left hand side and you can take the rest on the right hand side, and you can consider different points for x to get different points for y. But easy way to draw, to deal with this graph, is to put it into the intercept form. So in intercept form, what I do, we divide the entire part on the left hand side and the right hand side by the quantity present on the right hand side, and we get an equation of this form. Okay, you can call them as x by capital A plus y by capital B is equal to 1, where capital A is equal to C by A, capital B is equal to C by B, and this is called the x-intercept, and this is called the y-intercept. Okay, this is called the x-intercept and that is called the y-intercept. Now, if I do so here, in this particular case, you will find, interestingly, you are going to find that you don't have to bring this into intercept form because it is already in the intercept form. So considering those straight lines, considering them as equations only, considering them, these inequations as equations only, we can see that this particular thing is already in its intercept form, because it can be written as x by 1 plus y by 1 is equal to 1. And this is not in its intercept form, but can be brought by dividing all the sides by the requirement vector 4. So we can get x by 2 from here and y by 2 from there is equal to 1. So we have brought these equations in its intercept form. So let us draw this figure. So first of all, we are going to mark the points on the x-axis. This is 1. This do it some put it over here. This is 1, and suppose this is 2, and this is 1, and this is 2. Okay, now we are going to draw the intercept. We are going to join the intercept together. Okay, to get the straight line, the required straight line. So we are going to join them first of all. When we are joining these two intercepts, 1 and 1, we are actually drawing this straight line, x plus y equal to 1. So we can consider this as line 1. And when we join these two, we are actually getting the second straight line. So let us name those straight line as follows. We can consider those straight line as this is as line 1, and this is as line 2. Okay, so this is my line 1, and this is my line 2. Okay, now straight lines can stretch itself on both sides to infinity. So we can stretch this straight line to this end, and we can stretch that straight line to that end, but we are not going to do that, because if I do so, if I stretch them to this or to that, actually we are moving into the second quadrant and the fourth quadrant. But in these quadrants, in the quadrants second, third, and fourth, other than the first quadrant, at least one variable is negative. So we are not going to do that, because we know from the non-negativity restrictions that we have to be stick around the positive quadrant only to make the variables positive. So we are showing the positive half of the quadrant only. This is the reason why have I drawn this half of the graph. Second interesting part is that none of these are actually straight lines. They are actually inequations. But if linear equation, remember, let us write this point over here. It's a very important point. If a linear equation represents straight lines, okay, then their corresponding linear inequations represent regions bounded by these straight lines. Okay, and so we are going to mark those regions bounded by line 1 and line 2. Now listen to me very carefully. It is an important note. The note says that put the origin that is 0, 0 in the specified inequation. Okay, if the point 0, 0 satisfies the inequations, then the region bounded by the bounded by the straight line will be that side which contains 0, 0. If 0, 0 does not satisfy the inequation, then the region bounded by the straight line will be the side opposite to the side containing the origin. It's a very important point. I'm giving you 1 minute to copy it. I'm marking some interesting point over here. Put the origin in the specified inequation. If the point 0, 0 satisfies the inequations, then the region bounded by the straight line will be that side which contains 0, 0. If 0, 0 does not satisfy the inequations, then the region bounded by the straight line will be the side opposite to the side containing the origin 0, 0. So this is a very important note. If you have copied it, or probably you are clicking pictures of the screen, so hoping that I'm moving back to my previous slide to continue with the problem. Okay. So I'm moving to the previous slide. By keeping this rule in mind, we can see that if I put 0, 0 in this equation, 0, 0, then 0 plus 0 will be 0, which is less than or equal to 1. So it is satisfying the inequation. So the region bounded by this straight line x plus y equal to 1 will be the side which contains 0, 0. So the region will be this side. So I'm putting the shades over here like this. I'm putting the shades. And if I put the 0, 0 in the second equation, okay, then we see that this also satisfies the inequation, and therefore the region bounded by that equation will be the side containing 0, 0. So here also I'm going to get the region as marked by pink color, as you can see. But while marking the region, I'm being very careful not to cross the boundary and fall into the other quadrants, which are negative quadrants. So I have done my step 2. Okay, I have marked the regions. Now, in step 3, we are going to look into the common region bounded by the common region bounded by the two straight lines. Just a minute. Just a minute. Common region bounded by the two straight lines. According to the figure, I can say that this is the common region where the intersections of the blue color lined shades and the pink color shades had happened. And by looking into the common region, we mark the corner points of this common region. Okay, such a region is also called feasible region. Together they are known as common feasible region. Okay, because the values of x and y present in here in this region are feasible because they are non-negative. They become infeasible if they are negative. So therefore such a region is called common feasible region. So we have to mark the corner points here. The corner points mean the you know, in triangle there are 3 corner points, in square there are 4 corner points, in rectangle there are 4 corner points, in tetrahedron there are 8 corner points, like this. So we are marking this origin is marked as 0 0, and it's I have used the word alphabet O, capital O for origin. So here also we can use the alphabet capital A for this corner point, whose coordinate is 1 0, and capital B for this corner point whose coordinate is 0 1. Okay, so all the corner points have been marked as has been instructed. And step number 4 is that once you mark the coordinate, of all the corner points, we put their coordinates on, I shouldn't write their coordinates, I put the coordinates in the objective function one after another. One after another as follows. So what was my objective function? My objective function was z equal to 2x plus 3y. So I'm going to put all these 3 corner points over here. So I'm going to write it in the following manner. So first, number A is the value of z at the point, value of z at the point 0, 0. And what was the value? 2x plus 3y. So I can write it as 2 into 0 plus 3 into 0, which is equal to 0. Second, number B is z at the point 1, 0. Then we can put as 2 into 1 plus 3 into 0. Its value is 2. And number C is z is equal to 0, 1. So we can write it as 2 into 0 plus 3 into 1, which is equal to 3. Now, since it is a maximization type of problem, since the problem is of maximization type, we will consider the highest value of z, the highest value of z from the 3, and that is 3. This one, this is the highest value, and therefore the maximized value of capital Z is 3, which occurs for the points x equal to 0 and y equals to 1. And you are done with your problem. Now, some important portions which I'd like to mention over here are the following. First of all, the first important part which I want you to tell you is that why didn't I consider that problem which I formulated in the previous session? Why didn't I formulated that problem which I considered in the previous session? It is because in the previous session, the values were too large. I mean, 70 was there, 90 was there, 45,000 were there. I could have done that, but it could have taken some time because I had to change the scale and etc. and etc. Since you're learning this topic for the first time, some students are there who are learning this topic for the first time, so I didn't discuss. Otherwise, the motivation would have been lost. I would have been involved in changing the scale, because it is not possible to draw the graph with large values, and we in these situations we try to squeeze the scale and like this. So for these big values, I didn't consider the problem. Nowadays, softwares are available. If you are doing this sort of problem in the market analysis, then softwares are available by which you can do it very easily. Okay, so you don't have to be worried about that. But before you use a software, okay, you have to understand that what is running behind the screen, and therefore the mathematics which is running behind the screen. Because if you do not know the mechanics of something, suppose your car is your car's tire is punctured, and you don't have any idea to change the flat tire, then you don't have the you don't have any right to drive in the highway, because for this you cannot bring someone to help you in this situation. You will not be able to get someone. You have to learn it, how to change the flat tire. So softwares are available. Softwares can help you to solve the problem, but if you learn what is running behind the screen, then if flat tire like situations happen, then you can deal with that. Why? Second important part is that the values, you see that one important point is that why did I consider these corner points only? Okay, why these corner points have only been considered? So there is a theorem in linear programming problem which says that if you get a closed region bounded in the following manner, okay, these types of regions are actually known as convex polyhedron, and it is said that in the corner points of the convex polyhedron actually contains the optimum solution. Okay, so therefore actually this region is containing infinitely many possibilities for x and y, but we shall not consider those infinitely many possibilities. It is not possible. So a theorem is there which help us in this regard, and it says that you don't have to look for infinitely many possibilities in this scenario. You have to consider the corner points only. Deal with the corner points and you are going to get your optimality. And that's why I have considered this situation. Okay, and look at this problem. Maximize z equal to 2x plus 3y, x plus y less than or equal to 1, 2x plus 2y less than or equal to 4, x comma y greater than or equal to 0. Now, with little change in the form of the problem, you can get various other solutions of different types. So for example, I am giving you 1 or 2 problems which you can try at home. Okay, so these are actually homeworks for you. So you can consider the above problem where you change the word maximize to minimize. Okay, and put other thing as it is. So minimize z equal to 2x plus 3y subject to x plus y less than or equal to 1, 2x plus 2y less than or equal to 4, x comma y greater than or equal to 0. You are going to get a different, you have got a different problem, you are going to get a different solution. Take another problem. Say, for example, keep it as maximize. Z is equal to 2x plus 3y, subject to x plus y less than or equal to 1, 2x plus 2y greater than or equal to 4, x comma y greater than or equal to 0. Another solution you are going to get. Yeah, okay, previous slide. You will get everything in the note. Don't worry. I'll give you everything. Don't have to worry. My time is running out actually. You note down these problems. Okay. So I'm saving the board work. Board work has been saved. You are going to get everything. Don't worry. Third problem, you can consider maximize z equal to 2x plus 3y, subject to x plus y greater than or equal to 1, 2x plus 2y greater than or equal to 4, x comma y greater than or equal to 0. Okay, so these are three different problems which you can consider, and you are going to get different solutions. For the sake of your understanding, since I can give you a hint, the solution which you are going to get over here is like 0, 0. This here in these situations, you are going to get infeasibility, means solutions are not possible. And here, suppose you are going to get probably you are going to get unboundedness. Okay, so you can draw their graphs accordingly, and you can check whether these things are coming or not. I'm showing these different parts, different types of problems. It's because when we'll be doing the simplex method in the next class on Friday, then I shall deal with these problems once again. I will work on, I will apply simplex methods. I will work on these problems, not different problems, because by that time, the graphical solutions, the solutions will be available, solutions to the above problems will be available graphically. So once I apply the simplex method, you can compare whether you are doing it right or wrong. Once you are well versed with a simplex algorithm, then you can move on to the third level. That means you can take a problem with 3 variables and you can easily deal with that with full confidence. But in my past years in job, I have seen no students with full confidence in simplex method. Everybody is afraid of that. Anyways, so I hope that you will be solving this, you will try to solve these 3 different types of problems by yourself, to just have an idea about what are they giving. Okay, and in the last semester also you have set for online examination. In online examination, descriptive type of questions cannot be asked. Okay, small questions will be, questions like with marks 1 or 2 will be asked, but they may complicate the situation by asking you questions from the steps itself, from different parts of the linear programming problem. I can give you 4 different, I can put 4 different graphs in the options, and I can ask you which of the following is not a valid graph. Okay, understood. So therefore, this sort of questions can be asked. So you have to be very, very careful about this. Simplex method. You have to be very careful with the steps of whatever method you are doing. So don't think that sir is doing the descriptive, showing the descriptive mathematics, but we are going to sit for the online examination. These nodes which I have marked over here, these nodes, these steps which I've shown you, these are the regions from which questions can be asked. Okay, so you have to have a clear idea about what you are learning. I not kill further time in discussing graphical method in the next class. I am leaving these 3 problems for you. You can discuss among your friends. In the next class on Friday, I'm going to start the simplex method, and we have to move very fast because we are going to get less amount of classes in this semester. By the end of June, I'm putting some sort of target to finish the course. Okay, but you don't have to worry. Everything will be streamlined. You just follow my instructions. With this, I'm going to conclude my today's session. I thank you for joining my class, and we are going to meet in the next class, that is on Friday at 11:10. Till then, bye.